Right. This is the video on chapter 24. Hello, AP Stat students. And this one is going to go a bit quicker than the other two because we know what we're doing, and this one just goes by a little quicker. All right, so chapter 24, comparing means. You guys have your book out, pencil, paper, got your calculator. All right, let's talk through chapter 24. So again, we're just going to do a confidence interval and a hypothesis test. And you can add the chapter 24 interval and test. So it is the 2 sample t interval from chapter 24. The calculator command is 2 samp t int, and then we're going to do a 2 sample t test. 2 samp t test calculator command. So jot those down. This is going to be very helpful, all the different intervals and tests, because this year in the AP test, one of the 2 free response questions, you're going to have to do an interval or a test. And if you have them all right there with the calculator command, go to the one that you need. That'll be nice. And you can see in chapter 21, we did the 1 sample t interval, the 1 sample t test, just like in chapters 19 and 20, the 1 proportion, 1 proportion z interval and test. Then in chapter 22, we did the 2 proportion z interval, 2 proportion, 2 sample t interval, 2 sample t test. So chapter 24 is a lot like chapter 22, where we wanted to know, is there a difference between, the graduation percent in David Douglas and the graduation percent in Reynolds? Is there a difference? Or is one greater than the other? You could do in a hypothesis test. Comparing 2 proportions. So you find a confidence interval, you take 2 samples, and then you find a confidence interval for the difference. You're trying to capture the true difference in proportions. And if 0 is in the interval, then you can conclude that you can't conclude there's a difference, because the same thing minus the same thing is 0. But if it's not in the interval, it's like 2% to 5%, then you can conclude that there's a difference. And chapter 24 is the exact same thing, except not for proportions, but for means. Is there a difference between the average GPA at David Douglas and the average GPA at Reynolds? So take a sample of 100 David Douglas students, average their GPAs, 100 Reynolds students, average their GPAs. Find the difference between those 2 averages, that's your sample difference, and then from that sample difference, try to reach out and capture the true difference in GPAs. So it's really similar. So now that we understand the concepts, I think chapter 24 should be pretty smooth. And remember what's different about means. We're not using the normal model, no z-scores, no normal CDF, inverse normal. Now it's the T model, and we're using all the different T models, because the T model changes depending on the sample size, depending on the degrees of freedom, which is n-1. For 1 sample, it's actually different for 2 samples, the degrees of freedom. But just knowing that that T model is always changing depending on the sample sizes. And then the calculator commands inverse T instead of inverse normal, T CDF instead of normal CDF. And then when you do inverse normal, inverse T and T CDF, you always put a comma, the degrees of freedom at the end there. Okay, so let's do it. Let's get into chapter 24, comparing means. And why don't we do number 19 from the book? It's the one, it talks about the, it gets the data from 17, and in 19, we have to make a 95% confidence interval for the mean difference of runs scored in American League and National League games. So in 17, it gives us some values for the American League, and they're the average number of runs scored in some American League stadiums for the 2006 season. And then it gives us another data set for the National League, and it's the average runs scored in National League games. And then, is there a difference? Does one league score more games or score more runs? And I think the American League, they get a designated hitter, right? So they might, I would think that they score more, but I don't know. We'll see. Okay, so we have the data. Now, I actually have the data in my calculator already. So I put American League, 11.4, 10.5, 10.4. I put that in list 1. And then the National League, the 10.5, 10.3, 10. I put that in list 2. So you guys can actually pause the video and then put in that data. Put in American League and National League, list 1, list 2. And then let's write down what we're doing. We're going to do a 2 sample t interval. Name the interval, 2 sample t interval. Then check the conditions. All right, was it a random sample? And I'm going to put an X by that because it just says below are the average numbers of runs scored in American League and National League stadiums for 2006. So they didn't randomly select these averages. But, you know, is 2006 a good representative season? It could be. But I'll just say these averages were not randomly selected. And they should still have been randomly selected. But all right, 10%. Remember, you got to check that for both samples, 10%. So how many were there? Look at my list here. There were 14 and 16. So I'm going to say 14 averages. It's kind of a weird because we're finding the data values are actually averages. And then we're doing a 2 sample mean interval. So it's a little confusing, but I'll say the 14 averages 14 averages in the American League are less than 10% of all American League averages. And I got to say it for the other one too. 16 National League averages are less than 10% of all National League averages. It's kind of a weird problem because the data set are all averages, are all means. It doesn't always happen. Okay, large enough sample condition. So 14 averages in the American League, less than 10% of all American League averages. 16 National League averages are less than 10% of all National League averages. The large enough sample condition. All right, now this one can be a lot of work, right? Because you've got to draw the histogram. When? And remember, we want to see, is the sample large enough? Large enough to what? To use the normal or the T model now, not the normal model. And then if it's small, less than 15, it should be pretty unimodal symmetric. 15 to 30, little skewed, some skewness is okay. Greater than 30, we're good to go. Unfortunately, both of these, American and National League, are less than 30, 14 and 16. So you would need to sketch out a histogram on these. Why don't we just do that? This is often the hardest part. So stat plot, histogram, list 1. I'm going to hit zoom 9. So I'm doing the American League now. There it goes. Doesn't look great. Let's monkey with it, which you can do. So I hit window. All right. My X min is 8.8. I'm going to change that to 8. How about? And then my max is 11.92. I'll change that to 12. And I'm going to make my X scale 0.5. See what that looks like. That's a little better. That's actually not bad. 14 unimodal symmetric. I can make it a little better. I'll make it 1. Nah. 0.5. Oops. 0.25. You know, 0.5 is actually pretty good. Pretty good. It doesn't have to be perfect. I know it's less 15. It's less than 15, but that's unimodal. Yeah, it's all right. We'll go with it. Okay, then you quick sketch it out. Now, I would say American League, and I know this takes forever, and it is doubtful that they'll make you do this. Although there have been free responses, we have to do this. I don't expect it on this year's though. But I'm just gonna quick sketch it out. 8.5 to 9. 9.5. I know. Feel free to skip ahead while I make my histograms, because we gotta do it for National League too. All right, n equals 4 is my highest. I'm just using the trace button here, makes it a lot easier. That's unimodal symmetric enough. All right, so there we go. I'll show you that. That's my American League. Okay. National League, here we go. If you're good to go on this, feel free to skip ahead. That's fine. But it's good to talk through this together. This is actually the hardest, coming up with a window and stuff often for this unit. Okay, so stat plot on. Now I'm going to do list 2 instead of list 1. My histogram on list 2, doing a histogram of the National League. I'm going to write that down. National League. Zoom 9. And that's pretty good. Unimodal symmetric. There's a little gap there. But let's mess with it. Why not? Okay, my min, when I go to window, my min 7.9. I'm going to make it 7. 10.9 max. I'm going to make it 11. See if that does anything. Kind of skewed there. Yeah, it was actually better at first. That's pretty, okay. All right. Hold on. Ooh, that's pretty good. Pretty unimodal symmetric there. That's 0.2 scale, but I don't want to do all that. All right, I just made the scale point, let's just do 1. I'm just gonna make it 1 for the sake of, sorry. All right, you guys get the idea. Make the histogram, and then sketch it out. Okay. So here we go. Then what do we say for large enough sample? We're gonna say both samples are smaller, but, and then I'll put like n equals 14, n equals 16, but the histograms show they are unimodal and symmetric enough to proceed. All right, large enough sample condition, check. All right, so I said for the large enough sample condition, all right, I said both samples are smaller, n equals 14, n equals 16 in parentheses, but the histograms show that they are unimodal and symmetric enough to proceed. Check. All right, great. So random, 10%, large enough sample. And then the fourth condition is the same as the chapter 22 condition, the independent groups condition. Are the groups independent of each other? And let's just put a check on that. And we'll say the American League averages and the National League averages are independent of each other. So independent groups, check. Condition 4, the American League averages and the National League averages are independent of each other. And then I'll say, other than the random condition, all conditions met. Good to go. Okay, great. All right, that's the hardest part, doing the conditions. But you got to do them. You do have to do them. And I do expect one of the, so there are 2 free responses, a 15-minute, I think, and then a 25-minute. And I expect one of them to be a hypothesis test or a confidence interval where you have to check your conditions. All right, let's do the 2 sample t interval now. So name, conditions, do it on your calculator. So go to stat, over to tests, and go down to 2sampt enter. Now, do we have the data or do we have the stats? We have the data in list 1 and list 2. There we go. And you know, I didn't even see which one. I always like to do the bigger mean minus the smaller mean, just so we have a positive answer. So I'm actually going to quick crunch out the one variable stats on list 1. So it looks like American League had a 9.79 average. And then I'm going to quick crunch out the one variable stats on list 2. And the National League had a 9.4. Okay, so National League is lower, had a lower average from our sample. So I'm going to do the American League minus the National League to keep it a positive difference. You don't have to do that, but it makes it easier to write the conclusion and to interpret the interval. So back to two sample t interval. So I am going to keep list 1 for L1, list 2, L2. That FREQ 1, 2, don't even worry about that. And then we need a 95% confidence interval. And then it says pooled. No, yes. Don't pool. On the AP test, they do not want you to pool for means. We pool for proportions. And it doesn't even ask you to pool for a 2 proportions interval. It just automatically does it because that's the method. There's a pooling way you could do this too. You could read about it in chapter 24, but we don't do that. It's not on the AP test. So always just keep that as no. So you just want to put list 1, list 2, 95% confident, and here we go. Boom. All right. So our interval is negative 0.1658 to 0.88905, 0.8891. You probably just need 3 decimals, but and then what else do we have to give? What else do we always give? The degrees of freedom. Gotta give the degrees of freedom. And note that it's a decimal. It's not n-1 for 2 sample. It's 25.371. Give 3 decimals there. Okay, so that's all you need on the AP test. They will assume you did it on the calculator. Just give them the interval, give them the degrees of freedom. Okay, you don't have to show any work. And I'm going to quick check this answer just because I want to see that I typed the data sets in right. Make sure I didn't give you guys the wrong answer. Chapter 24, number 19. Negative 0.18 to 0.89. Negative 0.18. Wait, am I on the right? I got negative 0.165. Negative 0.17. The other one looks okay. Huh. 2 samp t interval. I don't know why that is. Yeah, it's close. I think we're fine. I think we're fine there. 2 samp t int. List 1, list 2, 95% confidence. Oh, we're good. We're good. Okay, so let's interpret the interval. Interpret the interval. We are 95% confident, and I'm going to steal their language, that the true mean difference between the mean number of runs scored in American and National League games, and I'm going to put in parentheses American minus national, just to say we did that one minus that one, is between negative 0.1658 and 0.8891. All right, so here's our interval interpretation. We are 95% confident that the true mean difference between the mean number of runs scored in American and National League games, American minus national, is between negative 0.1658 and 0.8891. Sorry for my handwriting, but you can hear me say it, so you're good. Okay, that's confidence interval. So did we conclude that that the National League or the American League scores more runs, or that there's a difference? And the answer would be no. Why? Because 0 is in the interval, right? Okay, so that is the one sample t interval. Let's do a one sample t test. Now, we're not going to go through like the bare bones of the interval, like the sample difference, the point estimate, plus or minus the critical value, the t-score, times the standard error, the standard deviation. And the reason why is because you're not expected to do that by hand. In order to do that, you need to know, what t-model am I using? And I'll just show you guys on page 562. You can see in the little footnote, that is the degrees of freedom formula for a two-sample means problem. It's not n-1. It's that crazy formula. It's not even covered on the AP test. That's why it's a footnote. So the two-sample t mean problems, you're going to do on your calculator no matter what. We don't have the tools to do them by hand, or they don't expect you to do it by hand. Okay, let's do a two-sample t-test now. And why don't we do number, let's see here, 27. Okay, here we go. Hungary. Researchers number 27 are on page 584. Researchers investigated how the size of a bowl affects how much ice cream people tend to scoop when serving themselves. In Ice Cream Social, people were randomly given either a 17-ounce or 34-ounce bowl, both large enough that they would not be filled to capacity. Then they were invited to scoop as much ice cream as they liked. Did the bowl size change the selected portion size? Here are the summaries. So we don't have all the data, but they did tell us there were 26 sample size for small bowl, 22 for large. The mean for the small bowl is 5.07 ounces. The mean for the large bowl was 6.58 ounces. So it does look like more people scooped, or people scooped more into the large bowl. And then the standard deviation, 1.84 and 2.91. Test an appropriate hypothesis and state your conclusion. And to the question, did the bowl size change the selected portion size? Assume any assumptions and conditions that you cannot test are satisfied. Let's talk through them. We won't write them out because it says assume they're satisfied, but we're still going to just talk through them. Okay, here we go. So we're going to do a two-sample t-test. Write that down. Name it. Gotta name it. Then check your conditions. And often on the AP test, it will say, assume the conditions are satisfied. Okay, first, random. Was this a random sample? Well, this is not a sampling from a population situation. This is an experiment. They were randomly given the 17-ounce or 34-ounce bowl. So random, check. They were randomly assigned treatments. That's a good thing. 10% doesn't apply. It's an experiment. Large enough sample. Now, N is 26 and 22 for this. So we would need to make a histogram, but the problem is we don't even have the data to make a histogram with. It just gives us the mean and the standard deviation of the samples. So I would say if you run into this, which you could, I would say I would put large enough sample, question mark by that condition, and say the sample is less than 30, so the sample should be unimodal symmetric, fairly unimodal symmetric if it's greater than 15. But since we don't have the data, we can't know, question mark. And then at the end, you could say large enough sample condition not met. Results might not be accurate, is what I would say for that. Because both samples are less than 30, and we don't have the data to check the shape. So that's a question mark for large enough sample. Independent groups, we have no reason, or the small group and the large group people are independent of each other. Check. Okay, we're good. All right, so we are going to then assume those are good to go. And again, we can just go right to our calculator because we're not going to use the sampling distribution because we don't know what t-model to use because that degrees of freedom formula is pretty crazy. So you're just going to do it on the calculator. So we go to 2samp t test, 2samp t test. All right, we don't have the data, we have the stats now. And then, okay, x1, sx1, the mean and the standard deviation. I'm going to do large minus small to keep it a positive difference. So the mean for the large bowl is 6.58 with a standard deviation 2.91, sample size n 22, type that in. And then the mean for the small bowl is 5.07 ounces, standard deviation 1.84. Sample size 26. That's what I typed in. 2samp t test. Okay, keep scrolling down. And we want, the hypotheses. We do need to write our hypotheses. We didn't do that yet. Okay, so let's write that down. Name, condition, hypotheses. So the null. The null is always, same as chapter 22, the null is that there is no difference. They are the same, no difference. So I'm going to say the mean for L, large bowl, equals the mean of S, small bowl. That's my null. They're equal. The mean of the large equals the mean of the small. And then the alternative, look at the question, did the bowl size change the selected portion size? And I would think that you would want to say, oh, we're going to see if they scoop more in the large bowl because it's larger. But it doesn't really say that in the question. It just says, did they change the selected portion size? It doesn't specify which way it changed. And I did look in the back of the book quick on that, and it does give a not equals to there. So we'll do that. It just says, did the bowl size change the selected portion size? Not did they scoop more in because it was a large bowl? Although it seems like that would be how you would want to do this problem, but we'll go with the not equal to there. And then make sure you define each of those. You got to define those, the mean of L and the mean of S. So that is the mean, really quick here. The mean number of ounces people scooped who got the large bowl, and the other one is the mean number of ounces people scooped who got the small bowl. Make sure you define those things. Context for your hypotheses. Mean number of ounces people scooped who got the large bowl. Mean number of ounces people scooped who got the small bowl. All right. Name, conditions, who they said we didn't have to check. We talked to them. Hypotheses. Now we can do it on our calculator. All right. So here we are. So we did a not equal to. We did a two-tailed. So click that. And then we never pool. Whenever it says that pool, just keep it. Don't touch it. And even if you think on the AP, oh, didn't we pool for a two sample? For proportions, we pooled. And it doesn't even give you the option. So always keep that no. All right. There we go. Okay. What do they need? What must you report? You must give them the critical value, which is not the z-score. It's now the t-score. They must have the t-score. T equals 2.104. And the p-value, of course, got to have that p-value, 0.0428. And what's the other thing you always got to give? The degrees of freedom. They need the degrees of freedom for these means problems, 34.313. Okay. Kind of messed up there. Okay, so that's what you gave them. The t-score, the p-value, the degrees of freedom, right off your calculator. T-score, p-value, degrees of freedom. And we are ready to state our conclusion. Okay, how about we do alpha equals 5% again? Does it specify? It doesn't. Okay. So here's our conclusion. Using alpha equals 0.05 with a p-value, so 4.28%, 0.0428 with p-value so low, less than 0.05. With a p-value so low, we reject the null. There is sufficient evidence for the alternative. There is sufficient evidence. I'm going to steal their language. There is sufficient evidence that bowl size changed the selected portion size. That's kind of how they phrase it in number 27. Using alpha equals 0.05 with a p-value so low, we reject the null. There is sufficient evidence that bowl size changed the selected portion size. And that was a close one with the 4.3% p-value. Because if we did alpha equals, if we had a 1% significance level, then we would have failed to reject. But at a 5% significance level, we did reject. And that's everything you need right there, including the conditions if it doesn't say they are satisfied. Okay? And again, we're not going to draw the sampling distribution. We're not going to crunch out the standard error. You're good because we're not, we don't know the degrees of freedom. You're not going to be able to get that 34.313 degrees of freedom unless you do it on your calculator. So they expect us to do this on the calculator. So we'll just do it that way. All right, that's it. Why don't we, quick, I know I want to keep these short, but let's quick interpret the p-value and interpret the confidence level on these two, just because got to be able to do that. Okay, so let's interpret the p-value, interpret the p-value. If the null is true, if there is no difference in the selected portion size between a small bowl and a large bowl, then there is a 4.28% chance that we would have got our observed difference in our samples due to sampling variability. I'll say that again. If the null is true, if there is no difference in the selected portion size for large bowls or small bowls, then there is a 4.28% chance that we would have got our difference from our samples due to sampling variability. All right. And now let's interpret the, let's go back to our interval and interpret the confidence level. Interpret the level. What does 95% confident mean? So not interpret the interval. We already did that. You got to do that every time. Now, no, interpret the confidence level. What does it mean to be 95% confident? Well, if we took repeated samples of, of National League and American League games, whatever sample sizes they were, 14 and 16. If we took repeated samples of 14 American League games and 16 National League games, then 95% of the intervals made from those samples will capture the true difference in the mean number of runs scored between American and National League. Okay, say it one more time. If we took repeated samples of American League and National League games, then 95% of the intervals made from those samples would capture the true difference in the mean number of runs scored in American and National League games. So just remember, you're capturing the true difference in means. All right, I think that's that. Well, thank you again, everyone. I hope you're enjoying these videos. I'll try to keep them coming.